All right. Hi, everybody. This is worksheet 3 on capacitors. I'm going to need to go back to the Blackboard situation. I'm sorry. It just has to do with the fact that the iPad I thought was fixed is still broken. So I'm just going to try to be very clear, and you can always message me with any questions. So this is just dedicated to capacitors, and capacitors is very important to be clear about your definitions and when to use which equations, and then recognize the interconnectedness of this. I guess the only other thing I'd want to add is just be very careful and clear with when you draw your systems of simplification. Okay, so I just want to start off with what a capacitor is. A capacitor consists of two conductors electrically isolated from each other and their surroundings. And the important thing to note is that a capacitor stores its charge in the form of an electric field. So it's almost like a pseudo battery, right? So you can almost imagine it like a battery. There's going to be like a side where the plus charge builds up and where the minus charge builds up, and it's going to have a voltage drop, just like a battery. But we'll talk more about that probably next week. And there's two methods of calculating capacitance. So this is probably the one you guys are more used to. And then there's also this version. So in this upper equation, let's call that equation A here, we have Q, which is the charge that is stored. We have V, which is the voltage across the capacitor. And then C, which is the capacitance of the capacitor. And that's in farads, right? And then looking at the one below, again, we have the capacitance of the capacitor as C. K is the relative permittivity, which is always 1 in vacuum and air. So you can just treat it as multiplying by 1, right? And the next thing is that E naught, which is the permittivity of free space. That's a constant that is 8.85 times 10 to the minus 12. Then we have S, and that is the surface area of one plate. And then we have D, which is the distance between the two plates. So we've kind of gone over the variables in these two equations to calculate capacitance. And then one of the most important things of this worksheet is recognizing parallel versus series, and then how you can combine them when they're in either of those two orientations. So in parallel, you simply add the capacitance values, you add them together. And with the in series situation, you will do that inverse addition. And let me just stop the share here and let you guys see the video. There's a quick way to do inverse addition when you're dealing with two terms. All you do in that situation is you do C1 times C2 divided by C1 plus C2. So someone, I showed you guys this trick and someone asked me a question. They're like, I saw him doing this in class. What does this mean? It's a quick way of doing that inverse addition. So that will be for when, they're in series, right? All right, so back to the sharing of the screens. All right, sharing again. Okay, so parallel and series. The next thing is when capacitors are in series, they have the same charge. When capacitors are in parallel, they have the same voltage. And in this, even though that's what these blanks are for, I really want you guys to fill this out. So again, up here, charge and then voltage. In series, they have the same charge. And in parallel, they have the same voltage. This is very important. It's going to be necessary to solve all the types of problems you're going to use this for. And it's going to enable you to make claims of a capacitor before and after it's connected to a battery, as we'll see on example number 3. Okay, now there's a few things I also want to know. So certain qualities related to capacitors remain constant whether or not the capacitor is connected to a battery or not, right? So they'll give you situations where the capacitor has been connected to the battery for a long time. It was just connected. It's been connected for X amount of time, whatever. All you need to know, or the important thing to note here is if it's connected to a battery, the voltage is constant. If it's disconnected from the battery, the charge remains constant, right? So that will allow you to make statements on those kind of scenarios. You can do you think about so when it's disconnected from the battery, the charge before is going to be equal to the charge after. It's almost like a conservation of charge, if you remember from conservation of energy. And yep, this is how you quickly do the inverse addition. And then the last thing I want to talk about is recognizing the one second, let me pause the recording and answer a question. The last thing I want to recognize is determining when capacitors are in series versus parallel, because obviously this is kind of the cornerstone of these types of questions. Capacitors that are in series, so they're on the circuit and they're in series, have no junctions in between them. And by inverse, those that are parallel do have junctions between them. And what a junction is, I like to imagine it as the current, the current flows through these electrical circuits. I imagine that current as if it's a water current. A junction represents a point where that current can diverge any number of ways. So if it's in series, there's no way, it will always be going the same way. There's no junction. If there is a junction, it has a chance to split, and therefore you treat them as in series. When you're simplifying these complex systems, let's look at this example right here. There's so many, and it's difficult to assess where to start. You almost want to start as far away as possible and then simplify in, right? So in this case, you would look at these three and say that, oh yeah, there's no junctions in between where my clicker is, right? So here, here, and here, the current will be able to go all the way through without any junctions. Therefore, they're all in series. Okay. So that kind of, let me just double check my notes. Yep, that sums up everything I wanted to address with respect to the notes. I'm going to stop sharing my screen here and then begin question number 1. Okay, so in question 1, it's on my phone. Let me, I'll be reading from here. So we have the 4 capacitors as shown in the figure, and they're initially uncharged when the switch S is open. We're given the capacitance of all those capacitors. A potential difference of VA minus VB is 240 volts, and it's applied between points A and B. So that means if you trace an arrow between the final position, because final minus initial, so final is VA, initial is VB. If you trace an arrow going like looping backwards through that system, you'll see that there's a 240 potential difference there. So then in part A, we're asked to determine the potential difference between points C and D. So we'll know that we'll need to find the equivalent capacitance first, right? Because if we look at everything, this entire system is in series. So let me draw that real quick. Here, I'll pause the recording as I draw, because these do take. All right, we're back. If we look at all of these capacitors, the only thing in between them is this system. It's a wire that's open. You treat a wire that's open as if it's not even there, right? No current's going to enter this way. So this, in fact, right here is not a junction. So rather, we're going to circle. I like to use circle for series and boxing for in parallel. I'll show you that later. We're going to circle here and call these guys in series. Because they're in series, we're going to do that inverse addition to find the equivalent capacitance, as by combining all of these, we're only going to have one capacitor left, or one effective, like quote unquote, effective capacitor left. So it's going to be the equivalent capacitance. So what we can say is 1 over the equivalent capacitance is equal to the inverse addition of all of them. So it'll be 1 over C2 plus 1 over C1 plus 1 over C2 plus 1 over C1. We can just do some simplification. We'll see it's 2 over C2 plus 2 over C1. All right, factor out the 2. I'll show you all the steps on this one, but I'll skip them on the other ones once you do the math on your own. This, still see? Yeah. And then you're going to find the reciprocal, because remember, it's 1 over the equivalent capacitance. So then the equivalent capacitance comes out to be equal to 0.1, 2, 3, 4, 5, 6. That's 6 zeros. 6, 7. All right. So now we have an equivalent capacitance. To find a potential difference between points D and C, we have to kind of, like draw in this arrow, right? Because, it's going to be that final position. So VC minus initial. Whenever they're written like this, that's the order. Okay. And because capacitors in series, by definition, have the same charge, and all of these guys are in series, we know that the charge at this C2 and at this C1 is equivalent to QEQ. So first, let's find QEQ. I'll write that here. So QEQ is equal to CEQ V. We don't know, we don't know the voltage here, right? Like the potential difference here. So we need to use this first arrow. And that's the potential difference between B and A. And that's given as 240. So QEQ is equal to, our decimal here, so 0.000067 times 240, and that equals 0.000161. Okay, and that's coulombs. And again, all of these capacitors are in series, so they all have the same charge. So that means when we're looking for VCD, I'm going to continue that down here, where VCD is equal to, VC minus VD is equal to Q EQ over capacitor 2 minus Q EQ over capacitor 1. Again, the charge at all of these are the same. They're in series. That's by definition. What's, V is equal to, as Q is equal to CV, V is equal to Q over C. That's what we express here. So VC, let's call that this position, or this position, because it doesn't matter, right? Whichever one you want to do it, whichever order, is equal to that fraction over that fraction. Okay. So then you plug in all your terms, and you get 120.75 volts. All right, that is part A. And then in part B, we're asked to determine the charge on each capacitor after the switch is closed if the potential difference between points A and B remains the same. So in this situation, I'm just going to do a quick draw here. A, and this is B. The switch is now closed. We want to figure out what the charge is on this set of capacitors and on this set of capacitors. So the current entered, effectively there's a battery here, right? The current's coming from something. It's not just coming from nothing. So you can imagine there's a battery here that releases a current into the system. The current travels along, hits this first capacitor, and continues traveling along. At this point, the current will only go down the wire. And the reason is this is because the current will always go the path of least resistance. So in the case there's nothing else here, there's no capacitor, there's no resistor, there's nothing else here, it will continue only this way. Therefore, no current is traveling through these two. So we can say to the capacitors to the right of the wire, to the right of the switch, the charge is equal to 0. So I'll say Q, and I'll say RS here for right of the switch is equal to 0. And now for the left of the switch, that's a different question, right? We now need to consider these two systems. There's a junction there, or I'm sorry, they're now in parallel. So we need to box these guys. They're in parallel. So, wait, sorry. These guys aren't in parallel. Scratch that. Sorry, I got mixed up. I just said, there is no junction here. That's why the current doesn't continue there. The current only goes one way. So again, they're in series. And this was C2, and this is C1. Therefore, we can find the new equivalent capacitance as C2 C1 over C2 plus C1. That comes out to be equal to 4 over 3 microfarads. Okay. So let me just be absolutely clear here. I hope everybody started the recording. Oh yeah, I did. Let me be absolutely clear. These two are in series. I said there was a junction. There is no junction here. The current only goes one way. That's what tells you the charge on these two is equal to 0. And yeah, the current only goes past the least resistance. Okay, so now we have the new equivalent capacitance. Let's call that CEQ prime. And we can find the new charge, QEQ prime, which is equal to, CEQ V. They said the voltage stays the same, so it's 4 over 3 times 240. This value comes out to be equal to 320 microcoulombs. And I'll call that QEQ left of the switch, LS. Okay. So this is the whole problem. Verification. They're in series. It's not a junction as the current only goes this way. And does not enter the right side of the system. I'm going to pause the recording and take any questions. All right, moving on to question number 2 here. So now we have this circuit, right? And we want to determine the equivalent capacitance given the capacitors values of C1, C2, and C3. We have them all. And then we have parts 2 and 3, but we'll get to those later. So we're looking at this complex circuit, and we see a bunch of capacitors. If you remember the advice I gave you, I said you kind of want to start as far as possible and then work in. So in this case, as far as possible is these 3 right here. We look at this position, we look at this position, and this position. What we can observe is they're all in series. There's no junctions between them. So I'm going to do a soft circle, and I'm going to call it in series. Okay? Put an S up here. S for series. The next thing I like to do is draw an arrow. And on this arrow, I'm going to combine all of them. So for things in series, it's just that inverse addition. So 1 over C3 plus 1 over C2 plus 1 over C1. And if you do that math and plug everything in, CS comes out to be equal to 0.92 microfarads. And what I like to do is put quotes around it. Putting these quotes around it is specifically because we're going to condense the system. So effectively, what replaces these 3 capacitors is a single capacitor with a capacitance of 0.92. So I do like air quotes right there too, because there is truly no capacitor there that is 0.92. But when we simplify it, we can imagine it's there. So that tells you it's an imaginary one of a condensed, like it's a condensation of these 3 capacitors. So we then redraw the diagram. So we have this A position here, we have the capacitor, another capacitor, one here, another capacitor, this, I think there's one between, I missed one. One here, one here. Oh wait, that's right, like this. Just double check. Yeah. All right. And then this was the one I'm going to put my quotes on, 0.92. Oh, quotes, not parentheses. So now I have a condensed version. So I'm going to do is keep working from outside in. Between these 2, there's junction. There's a junction right here. The current can go either way. They're in parallel. So capacitors in parallel, we'll call that CP. You just add them up. So that's 0.92 plus C2. CP comes out to be equal to 4.92. I'm going to put that again in quotes because, it's kind of imaginary in that respect. So now I have A here, the capacitor. And then B, capacitor, like that. Where this is 4.92. So again, I want to clean this up, make it smaller. So I have these 3 working from outside in, simplify it. These guys are all in series. How do we handle series? We do the inverse addition just like we did in the first step. So what we'll say is 1 over CS is equal to 1 over 3 plus 1 over 4.92 plus 1 over 2. This comes out to be equal to 0.965. And again, I'm going to put that guy in quotes. We redraw the diagram again. So here's our A, and here's our B. Except at this position now, we have 0.965. All right. Looking at this, we see the junction here. Again, we're working from outside in. Junction right here. These guys are in parallel. What do? We just add them up. So adding them up, oh, the cheer here, nice. We get, how should I do this? I can fit. So CP is equal to 0.965 plus, what's that, 4? So CP is equal to 4.965. That guy encodes. I'm going to redraw up here. So combine these, what does our system now look like? We have a capacitor. We've combined these two, so a capacitor right here. And we have this last one right here. This should look familiar now as they're all in series. We combine them. Do that inverse addition like we have done now so many times. That's 4.965 right here on this capacitor. We combine them in series, and we're just going to now solve for the equivalent capacitance, right? Because at this point, as you simplify these three, you're only left with the one more capacitor left. And that one last capacitance will have the equivalent capacitance. So that's going to be equal to, let's see here, 1/3 plus 1/4.965 plus 1/2. That comes out as right here, 0.97 microfarads, CEQ. Okay, so you can see we just simplified from the furthest position in. We did like a series, then a parallel, then in series, and then in parallel, and then in series to get the final capacitor, which then has its equivalent capacitance by definition. So that's part A done. The next part, in part B, we're asked to solve for the charge on the capacitors C1, C2, and C3, which are closest to points A and B. So that's where I'm putting the little stars right here. I'll do little stars. We want to find the charge on these three capacitors. So what we'll have to do is first find the QEQ, right? That charge in comparison to the equivalent capacitance. So this is part B. I'm going to say QEQ is equal to CEQ times V, right? And they gave us the voltage, the potential difference between points B and A. So between points B and A is 200 volts. So we just got to plug in what we have. So that's 0.97 times 200. And that equals, what can't I read my handwriting? Sorry, one second. 194 microcoulombs. Okay. All right. So now we have the charge of, it's like at this point when we have the equivalent capacitance, it's effectively looks like this, right? Where that's A and that's B, and this is CEQ. So we have the charge of this position. But if you recall, capacitors in series all have the same charge. So if we look back at this diagram, we have three capacitors. We have this one that's in quotes. Oh, I'm blocking. We have this one that's in quotes, but that one doesn't, remember, that's an imaginary one. It's in quotes, right? And we also have this one up here and this one down here. This one is C3. It's this position, right? Remember, we simplify from out in. It is truly this position. And this one down here is C1. So now we know the charge at C3 and C1 as capacitors in series all have the same charge. So this value, QEQ, is equal to the charge at Q1, which is equal to the charge at Q3. Equals 194 microcoulombs. Oops, 194. Okay, so now which ones have we done? We did this one down here, we did this one up here. What's left is C2. So from this position, we're gonna need to continue working back outwards until we can get at a point that can comment on C2. So to do this, what we're gonna need to do is calculate the voltage shared by the voltage using QEQ of this position. So we'll say QEQ is equal to C, what was it, 4.965 times V. So a few things are known. First of all, this is also a part of this series of capacitors. So it does have that same QEQ, right? It has the same charge as Q1 and Q3. We also know the capacitance because we calculated that already. So to find the voltage at that point, that's QEQ divided by C, 4.965 is equal to V, where V in this case will then come out to be 39.07 volts. Okay, so now we found the voltage at this position. Remember that the voltage of capacitors in parallel are the same. So therefore, we know the voltage of this position, where this position here equates to this position. So now we can say Q2 is equal to, I think it's 4, right? C2 is 4. Yeah, so it's equal to 4, that's that capacitance of that position, times 39.07. Q2 is going to be equal to 156.3 microcoulombs. We have now found the charge at all those positions of interest. Check there. So again, the logic for that last one is we found QEQ. QEQ, is the charge here, which is equal to the charge here, here, and here, as they're all in series. We can find the voltage here because we already know the charge, and that voltage is the same between this position and this position as they're in parallel. Using that knowledge, we can solve for Q2. Okay, so that is part B. And leaving us with part C. So part C asks us to determine the potential between positions C and D. So C is right here and D is right here. All right? So how do we set this up? I'm going to erase part B because I don't want to get rid of my diagram. Okay. So between VC minus VD, that means final minus initial, we're going to call that as equal to Q. I'm going to call it double prime so we don't get it mixed up with anything else, divided by 4.92. So let's talk about why that is. 4.92 was the imaginary capacitance of this capacitor. This is the capacitor between points C and D. So you can imagine there's a D here and there's a C here, right? So when we do that final minus initial, so this part right here, I'm going to put a zigzag line around it. Sorry, it's getting a little messy. That part right here with this zigzag is equal to this part where there's the zigzag. Okay? So there and there are equal. Except now the difference is we have a cleaned up version and a means to calculate the charge. So the charge here is equal to 39.07. So that 39.07 was the charge we previously calculated for this capacitor, right? But remember, they're in parallel, so their voltage is the same. So therefore, we can implement the same kind of logic here, saying Q2 is equal to 0.965 times 39.07, and then Q double prime is equal to 37.7. And again, allow me to explain this. So we found the voltage of these two, which were the same, right? So we could find the charge at this position. That's Q double prime. The charge there is Q double prime. Whatever that Q double prime is equal to the charge at this capacitor, and this capacitor as they're in series. So using the understanding of that voltage, we found charge. That's the same charge that applies here. So now we can divide that by the capacitance of this position that is between positions D and C, and we can find the potential difference. That's equal to 37.7 divided by 4.92, which equals 7.66 volts. All right. So I get that this whole thing is kind of complicated because there's so much interconnectedness. So that's why I'm telling you, you should really do a good diagram so you can trace your steps back, define when they're in series or in parallel. That's how you reach the answer to part C. All right, I'm going to pause the recording and take any questions. All right, so now this is question number 3, our final question of this worksheet. So here we have a capacitor of a capacitance that's given. It's connected to a 20-volt battery. After the capacitor is charged, the battery is disconnected. The capacitor is then connected in parallel with a second capacitor of that capacitance. The second capacitor is initially uncharged. Determine the charge on the capacitor after they have, on each capacitor, so remember there's 2 afterwards, after they have been connected. So I want you guys to remember at this point that when they're disconnected from a battery, the charge remains constant. Therefore, we can make a claim on Q before is equal to Q after. Right? The charge stays the same after they're disconnected. So what we can say here now is C1, I'm going to call this V initial, because initially there's only that single capacitor, is equal to C1, the final V, plus C2, and that final voltage. We're going to have to rearrange some of this, just clean it up. Let's factor out as VF. We're left with C1 plus C2. At this point, we're going to want to solve for VF by itself. So we'll do C1 V naught over C1 plus C2. Close those parentheses is equal to VF. We can calculate VF as we know the capacitances they're given and that initial voltage. So VF is equal to 8.57 volts, right? We can now quickly find Q after relative to each capacitor through the equation. I'm going to call it QA, 1 for capacitor 1, is equal to C1 VF. And then Q after 2, QA2, is equal to C2 VF. You're going to plug in the relative capacitances, plug in VF, and what you're going to get is 51.43 microfarads and microcoulombs. And 68.56 microcoulombs. Yeah, so don't make the mistake I just did. Like keep your, with capacitance is units in farads, and then charge is in units of coulombs. So don't mess that up. And the point of this question is to demonstrate that important fact that, when capacitors are connected to a battery, the voltage is constant. And when they're disconnected, the charge is constant. And that allows us to make this relationship of kind of this conservation of charge before and after. And through that, we can find the charge on each capacitor after, they're unplugged. Okay. I'm going to stop the recording here. Thanks for watching. Let me know if you have any questions, and I'll take questions from the Zoom.